Welcome to today's colloquium. Very happy to have Dr. Raffaele and Marino here, and also thank you for coming in such a cold day. And some information about Raffaele. Raffaele received his PhD in physics from University of Nice and University of Calabria. It's a joint program between France and Italy. And he was studying scaling law in solar wind turbulence. And in the next few years, he worked at a few different places under research or teaching fellowship, including Catania Astrophysical Observatory, University of Calabria, and Institute for Space, Astrophysics, and Planetology at Rome. And he also taught at a technical high school in Italy. So he takes education outreach very seriously, you can see. And then he came to NCAR as a postdoc a fellow in 2012, and worked in NIC's turbulence numeric team. And his research interests include solar wind turbulence and the statistical properties of turbulence in rotating stratified fluids and plasma, which we'll look forward to hear more today.
Okay. Thank you. Morning, everybody. So I want to first thank Anli for inviting me to give this seminar within the HAO colloquium. And it is a pleasure for me to speak in front of such an expert audience today. So I'm going to talk about turbulence in rotating stratified flows. And turbulence is a phenomenon which is ubiquitous in the universe. It plays an important role either on planet Earth and also in the outer space. Stars, galaxies, and also the interplanetary medium develops turbulence, like heliospheric plasmas or solar wind. So it's a very a universal phenomenon. And I'm pretty sure all of you are familiar with the idea that turbulence it's a phenomenon which occur at intermediate or small scales. Well, when I say intermediate or small scales, I mean those scales where the field fluctuations, that can be the velocity field fluctuations or the magnetic field fluctuations, if we are dealing with plasmas, are comparable with the temporal fluctuations. So those are the scales where turbulence kicks in. But it is also important for the large-scale dynamics because nonlinear interactions happen not only at small scales, but the small scale and the large scales can interact nonlinearly and also non-locally. So another reason why it is important, the study of small-scale phenomena related to turbulence, is for the modeling, for example, either in GCM or WRF or heliospheric or space weather models, a bad or an inaccurate parametrization of the very small scales would result in a bad and inaccurate description of the large scales. So that's the ultimate aim of this kind of research. We do fundamental research to get insights on phenomena related to turbulence in order to provide information which are essential for the modelers in order to improve the model. So the results I'm going to present today are based on the work I've done in collaboration with Pablo Minini, who is chair of the Department of the Physics of the University of Buenos Aires. Dwayne Rosenberg, who is here today, is a computer scientist at the Oak Ridge National Lab in Tennessee. Corentin Herbert, who is ASP fellow at NCAR, and Annick Bouquet, senior scientist at NCAR and professor at CU here in Boulder. Of course, all the things I will be presenting today are based on the work that Jack Herring and also Yoshi Kimura have been doing here at NCAR since the last 30 years. So, yeah, so that's an outline of my talk. I will go through an introduction on basic theoretical features in fluid and plasma turbulence, and then I will give you I will talk a bit about results in solar wind turbulence to give you an example of MHD turbulence, and then we'll go to the core of the talk, which will be on our most recent results in rotating stratified turbulence. All right, so the simplest definition of turbulence is that it is a mechanism to transfer energy from large scales to small scales, but not necessarily, as we will see in the following. And it is due to the nonlinear dynamics of the Navier-Stokes equation or the MHD equation if we are dealing with plasmas. And the nonlinear terms in those equations are responsible for the redistribution of the energy among the various scales. So the Canva, the turbulence phenomenology is based, is the one of the Richardson cascade. And this Canva, this actual Canva from the Japanese painter Hiroshige, depict very nicely what happens in the Richardson phenomenology, where energy is injected at large scales, transferred in inertial range by nonlinear interactions between eddies, and is eventually removed from the system at small scales. And that happens when the nonlinear time and the eddy turnover time are comparable. And at this point, the energy is converted, the kinetic energy is converted into heat. And this is very important because there are contexts and settings where turbulence, together with very few other mechanisms, can be addressed and accounted for the heating of flows. For example, in the heliospheric plasmas, I mean, it's very well known that the plasma, there's some source of heating that slow down the cooling of the plasma as it expands, and one of the possible source of the energy is thought to be the turbulence. Can I have a pointer, Honey? Okay, so in 1941, Kolmogorov introduced the universality hypothesis, which is based on the idea that very far from the source and sink of energy, the characteristic of turbulence only depends on the energy transfer rate and on the scale. So with those two quantities, we can obtain a prediction on the spectral slopes of the kinetic energy spectrum, which is the very well-known Kolmogorov spectrum. So, but nonlinear interactions can happen either at small scales with turbulence mixing, dissipation, with the occurrence of very strong localized phenomena, but they can also happen at large scales with an accumulation of energy at a smaller k in the Fourier space through an inverse cascade. Okay, so this is the Navier-Stokes equation in 3D. In the invested case for a barotropic flow, that is to say that the density depends on the pressure. So if we take the curl of this equation, the right-hand side vanishes, whereas we can rearrange the left-hand side introducing the vorticity. This is just a render of a vorticity field in a direct numerical simulation of rotating stratified turbulence. And so this is an equation for the vorticity. And okay, in the particular case of the 2D turbulence, where the velocity fields only depend on Higgs and Y component, and by definition the vorticity has only the Z component, the stretching term vanishes, and therefore the vorticity is a Lagrangian invariant. It means that it is conserved along all the Lagrangian paths in the flow. So of course, if vorticity is a Lagrangian invariant, as a consequence, all the functions of vorticity will be globally conserved in the flows. And in particular, the moments of the vorticity will be conserved, and among which we have the entropy. So entropy is a quadratic invariant, and of course, in the invested case, energy is also a quadratic invariant. So the reasons for the occurrence of an inverse cascade in fluids can be explained using statistical mechanic arguments, and the idea is that when the system has more than one quadratic invariant, the equilibria that develops are not only an equipartition of the energy among the modes of the truncated system, but other solutions can develop that see a pileup of one of the two invariants at large scale. So, and this is the case, for example, of the 2D turbulence, where entropy and energy are conserved. So without invoking the statistical mechanics, we can see using this Fjordorf argument, which is a phenomenological argument, why, for example, in the 2D case, where energy and entropy are conserved, energy has to cascade toward the large scale instead of the small scale. So if theta is the entropy production rate, the relation between theta and the energy injection rate follows by the definition of entropy and energy. So it's going to be k square epsilon. And in a statistically stationary turbulence where either the energy production rate and the entropy production rate has to be equal to the energy and the entropy dissipation rate, what we have is that, okay, if we inject energy at kf, if the energy was dissipated at k plus, where k plus is much larger than kf, then we would have that k plus square epsilon would be much larger than kf square epsilon, which is which is equal to theta. That is to say that the entropy, the dissipation rate, will be much larger than the entropy production rate, which in a statistically stationary turbulence would be a contradiction. So for this reason, energy cannot be dissipated at k plus, but it has to go towards k minus. That's probably the simplest explanation for why in the turbulence, I mean, the energy cascades towards the large scale. All right, so oftentimes an isotropic system, strongly anisotropic system, shows a 2D-like behavior. This is the case, for example, of rapidly rotating fluids, or also is the case of plasmas. At this point, I wanted to make an analogy between those two systems because these two systems have a lot of common features. One of these is, for example, that Dave develops inverse cascade. Another is the presence of waves. And those are the MHD equations written in terms of Alsacer variables for the ideal incompressible case. So the Alsacer variables are very, very used by the astrophysical community because it's easy to take into account the Hafveni correlation combining the velocity and the magnetic field written in this unit. So those two equations, set of equations, are very similar from a formal point of view. I mean, let's assume that the rotating term is not here. They look very much the same. But actually they are not, because the nonlinear term in the MHD equations combines two different kind of modes, Z plus and minus. And this is a major difference because the linearized version of this set of equations would give two single wave equations which describe the propagation of the Alfvén waves. So this combination of the Alsacer modes is the one responsible for the presence of Alfvén waves in MHD. So inverse cascade is an analogy, presence of waves is another analogy. And, but what happens to the effects of waves on a turbulent systems, either on fluids and plasmas? So I like to start discussing the plasma case because the phenomenology, I mean, the first attempt to include the effects of waves in the phenomenological description of turbulence was done for plasmas, and is due to Hiroshnikov and Kriknen. So we know that in plasmas there are those, among other waves, I mean, in the incompressible case, there are Alfvén waves propagating in the opposite direction of the magnetic field. So the effects of waves on turbulent eddies is that of a sweeping of the turbulent structures. So in the classical Kolmogorov phenomenology, we assume that the maximum time that turbulent eddies have to interact each other is their own lifetime, right? So it's the eddy turnover time. But in presence of waves, the time that turbulent structures have to interact is smaller, and the reason is that by the time they try to interact, they are swept around by these waves. So that's an easy way to see what is the phenomenological pictures when there are waves in turbulence. So in order to take into account this effect, Hiroshnikov and Kriknen came up with these arguments, which is the following. So instead of using the nonlinear time in the classical Kolmogorov phenomenology, they use this ratio, TNL over theta, where theta is the ratio of the characteristic time of the waves and the nonlinear time. So if you plug this transfer time in the Kolmogorov phenomenology you do all the easy algebraic calculation, you end up with a different prediction of the spectrum of the turbulence spectrum. This is widely verified, for example, in astrophysical context. But the problem with the spectrum, generally speaking, is that either the Hiroshnikov-Krykman and the Kolmogorov spectra are phenomenological relation. That is to say that they only suggest the presence of turbulence in a medium, but they are not a rigorous proof of the existence of turbulence, of the fact that the turbulence cascade is in action in the fluid. They gave information only on the fact that those signals have some degree of correlations, and you can see this as a power law in the spectrum, but they don't really tell you, they are not a real proof of the presence of turbulence. What one can do to check whether, the signals you're dealing with are the effects of a deterministic process like turbulence is to check one of the most important results in turbulence, which is the Kolmogorov 4/5 law, which is an analytic relation obtained from the Navier-Stokes equation, and it's a third-order moment of the fluctuations of the velocity. So that's what we did in solar wind. So I wanted to provide just a couple of snapshots of these solar wind results as an example of MHD turbulence. So what we did was to try to verify the analogues of the 4/5 law for the MHD, which was derived by Hélène Politano and Annick Pouquet in 1998. So in order to do that, we used the data of the spacecraft Ulysses. Ulysses was the first spacecraft, was a joint mission, ESA and NASA, and was the first spacecraft which was able to measure the out of the ecliptic wind, so the fast polar wind, which is the best to use if you want to do high order statistics, because it's the one that is less affected by compressive phenomena, stream-stream interactions in the ecliptic plane, or effects due to the co-rotating interaction region. So what we did was to try to compute this correlator, the correlator of the 4/5 law for the MHD in the Ulysses dataset. Of course, the two movies are not synchronized, but that's the idea. I mean, we were scanning all the Ulysses dataset looking for this linear scaling, and because this linear scaling tells us that there is an actual turbulent cascade in action in the solar wind. And, but this scaling provides also another important information, which is this coefficient. I mean, when we make fits of this linear scaling, we can obtain an estimate of the energy transfer rate, which is not the case for the turbulent spectrum, where we don't know the constant in front of the energy transfer rate. So that's what we did. We first characterized solar wind turbulence with the Politano and Pouquet law, and then we did estimates, real estimates of the energy transfer rate of the MHD cascade, and then with these estimates we try to answer another questions, which is still open in solar wind, which is why the solar wind, the proton temperature of the solar wind doesn't drop down as an adiabatic law, which is what you would expect, because solar wind is a gas in free expansion. So it should follow an adiabatic decay, but actually from the '60s, it's very well known that the observed radial temperature profile is much slower than adiabatic. That is to say that there is some heating mechanism at work within the solar wind. So what we did was to compute this quantity, epsilon, and to look for correlation between the temperature measured in the places of the heliosphere where we were able to estimate epsilon, and what we found is a very, very good correlation between the energy transfer rate and the temperature in solar wind, which means that at least part of the energy that turbulence can take at small scales with a turbulent cascade is eventually dissipated and transferred to the solar wind. Even if we don't know which are the mechanisms the mechanisms by which this happens, because you know the solar wind is non-collisional, and so God knows what are the mechanisms by which the kinetic energy is eventually converted into heat. Anyway, so going back to neutral flows, this is the case of the Hiroshnikov-Krykman phenomenology applied to the case of a rotating system. So this is a fluid system with rotation. So TW is the characteristic time of inertial waves, but you can do exactly the same I showed for the MHD. So you use this transfer time instead of the eddy turnover time in the Kolmogorov phenomenology, and you end up with a new prediction for the kinetic energy spectrum, which is k to minus 2 instead of k to minus 5/3. So this is a simulation from Pablo Minini where he shows that turning on and off the rotation, you get the minus 5/2 spectrum in presence of rotation, or the minus 5/3 spectrum when the rotation is turned off. Okay. So,
sorry.
Yeah.
What was found?
Sorry?
What was found in that?
In this simulation? Okay. So this is a DNS, is forced here, I believe k equals 4 and 5. So the dashed line is the simulation with the rotation turned on. So it's probably Boussinesq with omega different from 0, so it's rotating. And the small scale spectrum, I mean the spectrum behind the forcing scale is k to minus 2, which is the Hiroshnikov-Krykman prediction. So when you turn off the rotation, you get k to minus 5/3, which is the usual Kolmogorov spectrum in case of homogeneous isotropic turbulence. Actually, you have another information here, because this is the flux. And when the rotation is off, there is no flux at large scale, so there is no inverse cascade. Whereas when they turn on the rotation, there is a constant negative flux at large scales. That is to say that there is, although the range of scales is not enough to well characterize the inverse cascade. I mean, you see that there is energy piling up here, and you see that also in the flux. All right. So what we did, and all the results I'm going to show you, are based on the Boussinesq equation. So the Boussinesq approximation works pretty well in atmospheres and oceans, and it consists in getting rid of the density fluctuations everywhere in the equations, but when they are coupled with the gravity. So we want to get rid of the sound waves, for example, but we want to keep the gravity waves. So that's the idea. So this is the Brunt-Weishaller frequency, this is the Coriolis parameter, so it basically adding the rotation and stratification result in adding two linear terms to the Navier-Stokes equation, and in this particular case you have the density, the fluctuation of density are only coupled with the gravity, and the density is assumed to be constant everywhere in the equation. So unlike the case, the homogeneous isotropic case, in presence of rotation and stratification, is not the vorticity conserved, like in 2D, in the 2D homogeneous isotropic case, but is the potential vorticity conserved. And the problem with the potential vorticity is that it carries a nonlinear terms, and this is a problem for people who try to apply statistical mechanics to infer information on the directionality of the energy in those systems, because I mean when you compute the second order of this thing, you end up with an invariant which is not quadratic, and that's a problem because they don't know how to get rid of these terms when they compute the partition function of the statistical mechanics, which is, I mean, the main ingredient of the statistical mechanical approach, because then you have then you want to derive the energy and other characteristic quantity of the systems using these partition functions, which has a non-quadratic term in front of one of the two Lagrangian multipliers, and it's awful. So all right, so the code we use is the geophysical high-order suite for turbulence, which was developed in our team by Dwayne Rosenberg and Pablo Minini, and is a pseudo-spectral code. It's de-aliased with the two-tiered rule, so it conserves quadratic invariance. So it's a very accurate code. It's highly parallelized. It was tested up to 98,000 processors, I mean, it's a periodic code, and the aspect ratio of the simulation box is 1. All right, so those are, again, the Boussinesq equation. And if we want to try, if you try to look for solution of the linear system of the Navier-Stokes equation, in the inviscid case for an unbounded or a periodic domain, like the one we simulate with GHOST, okay, so that's the general solution we have to look for. It's an expansion with this amplitude and this exponential. So we look for solution in terms of waves, of course. So if we replace this solution in the system and we write the system in a matrix form, we end up with this relation. But using the compressibility, we can reduce the dimensionality of the matrix, and the spectrum of this matrix will be this one. So 3 eigenvalues of this matrix, the 3 eigenvalues are 0, sigma k, and sigma plus sigma k and minus sigma k, where sigma k is the dispersion relation of the inertial gravity waves, which are due to the two linear terms we added to the Navier-Stokes equation. So those are the correspondent eigenmodes, and we have that one of the eigenmodes corresponds to a 0 eigenvalues. And this is the reason why those eigenmodes are called slow modes. They are also called vortical modes or PV modes, because from the conservation of potential vorticity derives that you get sigma equal, when you get, in order to have sigma different from 0, you need the linear potential vorticity to be equal 0 and vice versa. So those modes are the one which correspond to 0, to non-zero potential vorticity. On the other hand, the mode Z plus and minus, which correspond to the inertial gravity waves, don't contribute to the potential vorticity. So, in other words, in the linear case, you have that the systems allows these 3 solutions, and there is no interactions between the inertial gravity waves and the vortical waves. This is, of course, true only in the linear case. In reality, then you have the nonlinear terms which couple those two kinds of modes. Okay, so this is the controlling parameter in homogeneous isotropic turbulence. I won't spend time talking about the Reynolds number. Those are the controlling parameters in rotating stratified turbulence. So that's the problem we have when we try to simulate those systems. So we have, being a turbulent system is in itself a multi-scale system, but it also has a bunch of characteristic length scales. In order to simulate and to describe properly the systems, you would like to resolve all those scales, which is extremely hard, especially when you don't want to use models, as we do. So, in particular, I mean, you can define the Froude number and the Rossby number, which are a measure of the relative importance of the stratification and rotation versus the nonlinear terms. And then you have the buoyancy length scale, which corresponds to a Froude number equal 1. I mean, if you assume the Froude number is equal 1, you can derive the buoyancy scale, which gives you the width of the layers in a stratified system. And from the buoyancy scale, you can obtain, you can derive the Holtz-Meadow scale, which is the scale at which within the layers you recover isotropy. I mean, if you go down at smaller and smaller scale in the spectrum, even in a stratified system, at some point, you won't see anymore the stratification. So you recover isotropy at very small scales. So this scale is obtained from the buoyancy scale, assuming that the energy follows the Kolmogorov spectrum, which means that we are assuming that the that the system is again homogeneous and isotropic. So inertial scale is the equivalent of buoyancy, but for rotation, and the same the Zeeman scale. Zeeman scale is the scale in a purely rotating system, is the scale after which we recover isotropy. We don't feel anymore the effect of rotation. All right, so there are two possible approaches to study those systems. One is to try to do this heroic simulation. Although in this case, the hero was Dwayne, who gave birth this monster simulation. It's a 4,000 cube. It's a direct numerical simulation. So you see, those are all the scales you would like to resolve. And you maybe you want to also put a decade of scales between all these characteristic scales. So if you count, it's 1, 2, 3, 4, 5 order of magnitude, which is impossible to do with a direct numerical simulation. So you do what you can if you don't want to use models. So this is the isotropic spectrum, which refers to this simulation we just started to analyze this week. And you know, I put in the on this plot the four most important characteristic length scale, which are the forcing scale. We force at kf equal 2 and 3, Zeeman, Holzmiedhoff, and dissipative. It seems that something happened at Zeeman. You see, before the Zeeman scale, this is a compensated spectrum. Before the Zeeman scale, the spectrum seems to be the one of the Hiroshnikov-Krachman prediction, -2, and after it seems to be -5/3. But this is a very preliminary result. I just wanted to show you, to give you the flavor of one of the possible approach to study this problem, which is the one of increasing the resolution as much as you can. Okay, so the one I showed you before were the solution for the linear system. Of course, we can look for solutions of the nonlinear system of the same kind. So with an amplitude which evolves on slow times, which modulates waves, fast waves. So if we look for solution of these kinds, we can obtain a relation for the nonlinear term in the Fourier space, and this relation for nonlinear term is different than the usual relation we obtain in case of homogeneous isotropic turbulence, because there is this extra term. So in homogeneous isotropic turbulence, the condition, the triadic condition that the wave vectors have to fulfill in order to transfer energy among the spectrum is this one. Whereas in rotating stratified turbulence, or in rotating or in stratified turbulence, you have waves, and this implies that together with the usual triadic conditions on the wave vectors, you have another condition on the frequencies, which reduce a lot the number of triads that can move energy towards the slow modes, or the PV modes, or the vertical modes, which are, as I will show you in the following, are the ones which are more representative of the turbulence in the system. So when rotation and stratification are of comparable strength in a rotating stratified system, inverse cascade can take place, and the inverse cascade is associated with the geostrophic modes. Okay, the geostrophic modes are compatible with the PV modes. So the analogies between the slow PV modes, vertical modes, and geostrophic modes. It's not easy to be, it's not easy to explain why, but without going through the math, but that's the analogy. So that's what probably also Jack found in one of his papers. Okay, so we performed a parametric study of rotating stratified turbulence in order to investigate the onset of the inverse cascade in the Boussinesq framework. So authors found that for values n over f, where n is the Brun-Weishaller frequency and f is the Coriolis parameter, for values n over f larger than 1, the stronger is the rotation and the most efficient is the inverse cascade. That is to say that for a fixed rotation, increasing the stratification can only slow down the inverse cascade. So that's what authors found in literature. So what we want to show here is that actually the efficiency of the inverse cascade, so the creation of large scales, is not monotonic with n over f. So it will be clear in the next slide. So the parametric study we did consists of 17 runs, 14 at 512 and 3 at 1000 cube on 1000 cube grids. So they are all forced at small scales, which is, that is to say, KF 22 and 23 in the 512 cube simulations, and the 40 and 41 in the 1000 cube simulation. So Reynolds is 1000 for all the runs, and all the runs are forced with a 3D isotropic forcing. It's 3D in the Fourier space, and the initialization of fields doesn't really matter in this case because the runs are forced. So, but the potential temperature is initialized 0, and the velocity field is initialized with a random field. So this is the range of values of n over f we used, including the two extreme cases, the purely rotating and the purely stratified case. Okay, so this is the kinetic energy versus the eddy turnover, the time rescaled by the eddy turnover time for few of the run of the parametric study, for few of the value of n over f. In particular, we have the solid red line refers to the purely stratified run where there is no growth of the kinetic energy. And this is true up to, we ran this simulation for a very long time, and it didn't show growth in the kinetic energy up to 130 eddy turnover time. So the solid blue line is the purely rotating run, and it does show a growth in the kinetic energy. So then the two runs in the shaded area are the ones with n over f equal 2 and n over f equal 1/2. And those, for those runs, the kinetic energy is growing almost with the same slope. And then we have the last run is the one n over f with n over f equal 4, which does show a growth, but not as much as the two run in the shaded area. Okay, now for all run, we estimated the growth rate, we computed the growth rate by fitting these curves from 10 to 30, because the peak of the dissipation occurs over here. So we wanted to fit to estimate the growth rate after the peak of dissipation. Yeah. Oh, that's right. Yeah. So yes, this is, you mean this? Sorry, can you say it again?
The energy you were studying here, is that the energy corresponding to the large scale?
It's the volume average. It's the volume average. So it's the integral of the isotropic spectrum. It's the integral isotropic spectrum averaged over the whole simulation box. So this is the total kinetic energy. Yeah. Yeah. So, okay, so yeah. So what we did was to compute the growth rate of the kinetic energy for all the 17 runs. And here all the growth rates are plotted versus n over f. So the red triangles refers to the runs with a constant, with the same Rossby number, the black squares refers to the runs with the same Froude numbers. And you can see same value of n over f obtained with different combination of Rossby and Froude gives the same value of the growth rate. So it seems that the controlling parameter is n over f. Is neither Rossby nor Froude. This is true in particular for values of n over f larger than 1. Okay, so now I'm going to show the real result, which is the following. Okay, we start from the case n over f equals 0, which is the purely rotating case. And in the purely rotating case, you have this growth rate of the kinetic energy, which is different from 0. So it's what we were looking here. So kinetic energy is growing. So the first triangle refers to this line. So positive growth rate. So as we turn on the stratification, a moderate level of stratification produces a faster growth of the kinetic energy. And this is true up to n over f equal 2. So if we keep increasing the stratification for values of n over f larger than 2, the growth rate will decrease monotonically with n over f up to 0 in the limit of n over f equal infinity. So what happens is this. So in the rotating case, there is an inverse cascade with which has some efficiency. This efficiency grows if we had the moderate stratification, is maximal here, and then increasing further the stratification, it will kill the inverse cascade. So that's the idea. So the maximum values of the growth rate, so the maximum efficiency of the inverse cascade, is for values of n over f in the range between 1/2 and 2. This is a special range in rotating stratified turbulence because it's the range where triadic wave resonances vanishes. So it's the range where one of the two conditions I was showing before is never fulfilled. So this can be seen easily in the case n over f equal 1. When n over f equal 1, from the dispersion relation for the inertial gravity waves reduced to omega equal plus minus n. So this condition is never fulfilled. But in this paper from Smith and Walev, there is the generalization to the range 1/2 and 2. So in this range, there are no resonant waves. That is to say that only turbulent structures, turbulent modes can interact unimpeded by waves. And they are more efficient in transfer the energy at large scales. So that's why here we get the maximum values for the growth rate. All right, so but the growth of the kinetic energy is only one indication of the presence of an inverse cascade. Another indication comes from the analysis of how the energy is distributed among the various modes, so of the spectral analysis. So this is how the spectra are computed. This is to answer the Annelies question. So what is plotted here is basically the integral of the spectrum, where the spectrum is computed over the whole simulation box. So is the volume average of the kinetic energy integrated over all the wave vectors.
So how do you know this is from the small scale to the large scale? Where is that scale?
No, there is no notion of scales here. There is no notion of scale here. I mean, in this plot, you have only the energy, the kinetic energy of the system with the passage of time. There is no notion of scale. This is not a it doesn't give any spectral information. It's the kinetic energy of the system evolving in time. That's it.
You want to measure the scale to the large.
Yeah, that's what I'm going to, exactly. But okay, so let me sum up. So the first indication that there is energy going at large scale is that in a forced system, the global energy of the system is increasing. So instead of going toward the large scales and eventually be dissipated at small scales, it's accumulating in the system. And you see this from the growth of the global kinetic energy. So this is the first indication. There is energy which is not being dissipated at small scales. But of course, if you want to be sure that this is the result of an inverse cascade, you want to see how the energy is distributed among the scales. And this is what you do when you study the spectrum. So here, in this plot, you have this quantity plotted, which is how the energy is distributed among the scales. So this is the forcing scale, and this is those three lines. Okay, the third line is not really visible, so it's 1, 2, 3. Those three lines are the three isotropic spectra taken at late time for the 1000 cube simulation. And as you can see, I mean, we were injecting energy here, and those parts of the spectrum, so whatever is on the left of this peak, at the instant of time t equals 0 was not there. I mean, those energy piled up over the time, which means that as the system evolves, there was a transfer of energy toward the large scales. So, which is why the integral of the spectrum was growing in time. And this is what you see in the plot of the global, of the volume averaged kinetic energy, which is the plot you were talking about. So, not only you have the build-up of these large scales for the case n over f equal 2 and n over f equal 4, which are the solid black line and the blue dashed line, but this growth, this pile-up of energy is organized in a power law minus 5/3 inertia range. And that's the second indication that the growth of the kinetic energy you were looking at, it's an actual inverse cascade of energy. So this is n over f equal 2, this is n over f equal 4. The case n over f equal 2 is more developed at the same time that the case n over f equal 4, because in the range of values 1/2 and 2, the inverse cascade is more efficient. So at the same time, if you plot the spectrum at the same time of the kinetic energy, the inverse cascade for the case n over f equal 2 is more advanced, is more developed than the inverse cascade for the case n over f equal 4. So, but what is nice here, even though it's not really visible, is the spectrum of the purely stratified case, which is flattened out. So in the purely stratified case, you have some accumulation you have some transfer here, but it's not in the form of an inverse cascade.
What are we supposed to be seeing? Blank space or?
Sorry? No, it's not visible. There is a pale green line here.
See, well, you trace it back with the
Yeah.
That is okay. How does it go? Very small values. Okay.
So, sorry, Jackie.
F equal to 0 in that case. How does it go? Very small values.
This one?
Okay, you can't see that. I can't see that.
Yeah, okay. Okay, so I can try to draw the large scale spectrum with the pointer. So this is what the large scale spectrum in the purely stratified case does. So it's flat. So it's not a power law. It's flat. And this is the purely stratified case. And this is the case where there is no growth of global kinetic energy. So actually, this is also what Jack and Yoshi Kimura found in a very recent paper. In one of your 2012 paper, there is a flat spectrum like that in the purely stratified case. And this is attributed to the layering. So in the purely stratified case, we would say there is no inverse cascade, because there is no growth of the global kinetic energy, and the spectrum is does not show a power law. But there is another, even stronger indication that there is no inverse cascade in the purely stratified case, and I'll show you in the next slide. I'll show you now, by the way. Okay, so those three, okay, again, the purely stratified case is not visible. Here there is something. So this is the Rod-Strat case n over f equal 2. This is the Rod-Strat case n over f equal 4, and this is the purely stratified case. And this is the flux, by the way. So this is the flux of the total energy. So the flux of the total energy, which is the cumulative of the transfer function in the Fourier space. So if we build this thing on the 1000 cube simulation, Rod-Strat, purely Strat, we have that in the Rod-Strat case n over f equal 2, there is a massive and pretty much constant negative flux at large scales, at scales larger than the forcing scale. And this is also true for the case n over f equal 4, but again, at the same time, the n over f equal 4 case is not as evolved as the n over f equal 2 case, because for n over f equal 2, the inverse cascade is much faster. In the purely stratified case, there is some energy, some flux here, but it's not even comparable to these two guys, and it's not constant. So that's the reason why we say there is no inverse cascade in the purely stratified case, although it's not clear, and it's still matter of investigations. I mean, it's not clear at all what happened. Authors found that for very long time, integrating the system for very long time, at some point, you have some energy growing at the large scales, but it's not clear if it's just a piling up of energy or if it's an actual inverse cascade, which makes a lot of difference. I mean, so nothing we can say about the forward cascade, the direct flux, because since we have put the forcing K at Kf equal 40, we don't have enough separation scale at small scale. So the system is not very well resolved at small. It's not resolved enough to say anything on about the small scale spectrum. So this is the third indication that there is an inverse cascade. So growth of the global kinetic energy, power law spectrum, and a constant large scale flux in the rotating stratified case. Yeah.
What will it finally grow to, or can you never get there because you can't afford it?
Sorry?
Well, you have growth continuing. Is there an equilibrium ever achieved?
No,
You run out of computer time.
Oh, that's a very good question. So, but the reason why we didn't answer this question is that those computations are very, very, very costly. So you would have to wait that energy peaks at k equal 1 and see what happens afterwards. And probably at some point you will have to remove the energy from the system. You have to put some frictions, otherwise the simulation blows. I mean, there is no way to remove the energy of the system if you don't put some friction. If you would be able to run this simulation for a very long time,
Do these calculations have dissipation in them?
they have dissipation but not friction. Dissipation means small scale dissipation.
I mean, Weber-Stokes kind or something else?
Sorry?
Weber-Stokes kind? Or
Yeah. But the point is that we remove energy at small scale. We remove energy at small scale. Dissipation is not zero. I mean, it's fine. There is a finite small scale dissipations, but there is no friction at large scale. So you can dissipate the energy which goes towards the small scales. But your question was, what happens if we would run the simulation for a very long time and the energy is peaking at k equal 1, and what happens afterwards? And the answer is that afterwards you have to remove the energy, and the simulation doesn't have a mechanism to remove energy at large scales. So I don't know what would happen, but probably the simulation would blow up. That's my guess. Okay, so in order to figure out why the growth rate, the inverse cascade behaves differently inside and outside the range minus 1/2 n over f equal 1/2 and n over f equal 2, we decided to study the energy transfer between the 3D modes and the 2D modes. So what are the 3D modes? What are the 2D modes? Okay, 3D modes are the modes which corresponds to the full 3D space of the Fourier space. Yeah. So whereas the 2D modes are the modes that lives in the plane k parallel equals 0 of the 2D, of the Fourier space. So how to compute the energy which goes from the full 3D modes to the 2D modes? Well, we start from the transfer function as usual, integrated over planes. So if we discard this thing for a second, this first integral and the first and second integral gives the energy flux in planes perpendicular to the parallel direction. So, but if we fix k parallel equals 0, we will have all the energy that is transferred from the 3D modes to the 2D modes. So and that's what this quantity gives you. So it's the energy flux from the 3D to the 2D mode. So I want to make a comment here. When I showed you the linear system, the linear Boussinesq system, and we obtained the three eigenfunctions of the system, which we called slow modes or vertical modes and fast modes. Actually, in the purely rotating, in the case of pure rotation, so when there is no stratification, there is another analogy, and there's another thing that we can say about the slow modes, and is the following. I mean, in the purely rotating case, where the dispersion relation is this one, the 2D modes, the slow modes actually correspond to the 2D modes. In fact, the modes with sigma equals 0 are the modes for which k parallel is equal 0. So let me rephrase this thing, which is rather important. So in the purely rotating case, the slow modes are the vertical modes. And therefore, the slow modes are the turbulent modes, whereas the fast modes are 3D and are the wave modes. But this correspondence is true only in the purely rotating case. In the Rotstrat case, things are mixed up. Okay, but this is important because of what I'm going to show you now about this quantity. Because even if it's an approximation, but if I can, when I talk of transfer between 3D to 2D modes, even in the rotating stratified case, I can kind of say that it's energy which is going from the waves to the turbulence somehow, but not quite. So the correspondence is exact and exists rigorously only in the purely rotating case. All right. So we computed the transfer from the 3D modes to the 2D modes for all the simulations we performed. So this is an energy per unit of time. So if we normalize this thing by an energy, we obtain an inverse of a time, and we can further normalize this thing with eddy turnover time, and we obtain a kind of high-dimensionalized sine times, which sounds horrible, but that's what it is. So the reason why we want to normalize first by the energy and after by a nonlinear time is that we want to compare all these points. In order to do that, since the energy and the dynamical features of those systems are different, we need some normalization. So we start from pi 3D to D, we normalize by the energy at the forcing scale, and we normalize by the eddy turnover time. And what we obtain is a quantity which tells us how fast energy is transferred from the 3D modes to the 2D modes. So what happens is that in the range of n over f 1/2 and 2, the transfer between the 2D modes and the 3D modes is faster than outside this range. So the values are higher, but it's an inverse of a time. So the transfer in the range n over f 1/2 and 2 is faster. That is to say that more energy goes from the 3D to 2D, or even if it's not exact, more energy is going from waves to turbulence. That will be exact in the purely rotating case, not in the Rotstrat case. But that can give you an idea. I mean, more energy is available for the 2D modes in this range to cascade towards the large scales. And this is consistent with what people have found in the past. I mean, when I say that in the rotating stratified turbulence, the inverse cascade is associated with the geostrophic modes, I'm kind of saying that it's associated with the 2D modes or with the vertical modes, which are compatible with balance modes. So it's kind of tricky, but that's what it is. So in the range 1/2 and 2, the transfer is faster, and the sign in this case means the directionality of the energy. If it's positive, it's energy which is going from the 3D to the 2D modes. If it's negative, it's energy that is going away from the 2D modes. And that's what happened in the purely stratified case. You see, as n over f increase, this time, this adimensional sine times, is becoming negative, that is to say that in the purely stratified case, you have energy going away from the 2D modes, which are the one that are taught to cascade toward the large scales. And that's why probably we cannot observe an inverse cascade, probably. All right, so this is the last couple of slides of my talk, and those are our most recent results. So the simulation I showed you so far are forced at small scales. And I say that nothing can be said from this simulation on the small scales, because there is not enough room from the forcing K to the dissipation K. So what is not very well recognized in literature is that the Boussinesq framework can support a double cascade of energy. So, but this cannot be investigated if we force the simulation at two large scales or two small scales, because in both the cases we would not resolve either the large scales or the small scales. So we took advantage of the Yellowstone supercomputer to perform this very large scale simulation and force the system at intermediate scale in order to have just about 1 decade on the left side of the forcing K K, and enough room on the right side of the forcing K to resolve the double cascade, if any. So that's what we did. We performed 6 runs, 5 at 1,000 cube. All the runs are forced at Kf equal 10, 11. So you have 1 decade of scales at scale larger than the forcing scale. So 5 runs at 1,000 cube and 1 run at 1,500 cube. And this time we picked only 2 values of n over f equal 2 and 4. This is the range of values for the Reynolds. The Froude spans from 0.02 to 0.1, the Rossby from 0.08 to 0.2. The forcing is again 3D isotropic because we don't want to prescribe the system using other kinds of forcing like 2D forcing. And again, the potential temperature is initialized to 0 and the velocity field is initialized to random initial conditions. So, okay, then here we define the buoyancy Reynolds, which is a measure of the relative strengths of waves and turbulence. It turned out very useful in trying to characterize those flows. So the range of variation of the buoyancy Reynolds is from 2 to 80. Okay, so the reason why we picked n over f equal 2 and n over f equal 4 is the following. So n over f equal 4 is very interesting from the geophysical point of view because people found in the southern abyssal ocean at mid-latitude n over f equal 5. N over f is 100 in atmosphere, so which is very hardly achievable with direct numerical simulation. But 5, we can do that. So that's why we picked n over f equal 4. On the other hand, we wanted another case where the inverse cascade is faster, because these computations are very costly. So at n over f equal 4, which is outside the range where the efficiency of the inverse cascade is maximal, it takes a very long time for the inverse cascade to develop. So we wanted a case which was compatible with a realistic case, and we picked n over f equal 2 case where the inverse cascade is very fast. So we have hopes to have the energy peaking at k equal 1.
We asked you what the abyssal ocean is. Is that the deep below the thermocline? Or
Sorry?
what is the abyssal ocean? Is it below the thermocline?
I have no idea.
We don't know.
Yeah, that's a value we picked from literature. I mean, there are several estimates for this value, and I have no idea how they measure
I was wondering
it in the ocean.
if we could take a tour there.
Have no idea. I would like to, but I didn't. No, we were looking because the ultimate aim of these things, I mean, it's a simplified system, okay? It's Boussinesq, there is no chemistry, there are no fancy effect embedded in this system. It's just physics, it's incompressible, but even, quote unquote, even only playing with all these characteristic length scales and parameters, it's a mess. It's very hard. It's very hard to figure out how systems react when you change one or more parameters. So it's a simplified system, but it's very telling from this point of view. But of course, you are always looking for places of the parameter space which are compatible with real cases, and this is one of them. So, those three lines are the 3 spectra which refers to the 3 n over f equal 2 cases. So those are single snapshots, so those spectra are not average, so are taken at T over TNL equal 22. So this is the kinetic energy for these 3 runs, and these 3 spectra are taken here. It's a single snapshot of the 3 run taken here. This is the entropy, which is proportional to the dissipation. So the peak of dissipation occurs at 1.3, around T over TNL equal 1.3 in these 3 simulations. And these 3 spectra are taken at very, very, very far from the peak of the dissipation. So the first characteristics you can observe is that the large-scale spectrum, which was inexistent at t equals 0. So all this part of the spectra builds up over the time. If you take a snapshot here, you have nothing here. So this is an inverse cascade which developed over the time for the 3 runs. So the first things to observe is that there is an inverse cascade and it's minus 5/3. And this is pretty much the same results we had in the previous parametric study. What is new here is that now the small scale range, the small scales are well resolved, because we are putting KF here, whereas in before was here. So we didn't have enough scale separation on small scales to resolve the small scale. So, okay, so first thing, -5/3 at large scale. Second thing, the slopes of the small scale spectra changes with the buoyancy Reynolds. So the larger the buoyancy Reynolds, the shallower the spectrum. And it approaches to Kolmogorov as well. So the spectral exponents for the simulation, which the highest value of buoyancy Reynolds is 1.87, Kolmogorov is 67, 1.7 maybe with the intermittency correction. But the interesting thing here is the trend. The larger the buoyancy Reynolds, that is to say, the larger the Reynolds and the Freud numbers, and the shallower is the spectrum. So here I want to make a remark, and it's the following. I mean, in this spectrum, it's hopeless to look for, I mean, it's not hopeless, but it's hard to try to identify the characteristic length scale I showed you before. I mean, the Hodgsmidov, the Zeeman scale. I mean, you would like to recognize needs, spectral breaks here, but it's very hard because all those characteristic length scale are defined in the purely stratified case or in the purely rotating case. Here things are mixed up. But there is an idea which is important, and is the following. The higher the buoyancy Reynolds, so the more I push those characteristic length scale towards the small scale, so the more I resolve the small scales, and the more the Kolmogorov phenomenon turbulence appears at small scales. So that's the message of this spectrum. So this is an actual dual energy cascade. And again, we want to see this not only looking at the spectrum and at the kinetic energy, but we want to check that also looking at the fluxes. And those are the fluxes. So again, unlike the previous parametric study, now we have a constant flux either at small scale and a large scale. So those are the 6 run, and all the 6 run has a pretty much constant flux at small scale and a large scale. So in this case, we were also So in this case, we were also able to estimate the value for the direct and the inverse cascade fluxes, and to estimate the ratio. This pi is the ratio of the fits of these fluxes at large scale and small scales. So, and what it turns out is that the larger the buoyancy Reynolds, the smaller is this ratio, and the ratio itself approaches to 1. So I forgot to show you this. This is the plot of what I was trying to say in words. So those are the spectral exponents of the small scale spectrum versus the buoyancy Reynolds. So the larger the buoyancy Reynolds, the shallower is the spectrum, and the spectral slopes, the slope approach to -5/3, which is Kolmogorov. Here, the larger the buoyancy Reynolds, the smaller is this ratio, and the ratio itself approaches to 1. So this is a vertical slice of the vertical component of the velocity, and I put this mark. This is roughly the forcing scale in these units. So as you can see, if you look at the zoom of a small portion of these flows, you can recognize features which are at scales much smaller than the forcing scales. That is to say that there is energy which is going at small scales and is creating small scales, which is a direct cascade. But if you look here carefully, you have also a large scale organized pattern. So unlike the previous parametric study, the previous simulations, here we have both evidences of small scales and of creation of small scales together with large scales. So, and that's, I mean, that's an indication, a clear indication of a dual cascade. Actually, we have also, I mean, the most resolved run here is a 1500 cube, but we also have a 2000 cube, which was not ready by the time we published these results in PRL, so it's not in these plots, because those are taken from the paper. But actually, we have another run, a 2000 cube run, which is even more resolved with a higher value of buoyancy Reynolds. And again, the spectral slope at small scale is even closer to Kolmogorov, and the ratio is closer to 1, which is about 1. Okay, so how much time I have? Minus 50, I'm sorry. Okay, so I'm done. This is the last slide. Okay, I could have put several bullets on this last slide, but I'd like to mention this project we have with Lee and other people here at the HAO, which is about the characterization of the wave turbulence interactions in the MLTE. So, I mean, with the computational power of the current supercomputer does not allow to resolve from the planetary scales down to the inertial range. But as I was mentioning before, there are places in the atmosphere and there are not natural settings where we are already able to address, to simulate with DNS. And this is the case of the MLTE. In the MLTE, the Reynolds number is 10 to the 3, 10 to the 4. And many of the simulations I showed you have Reynolds number 10 to the 3, 10 to the 4. So we can already actually perform direct numerical simulation of real context. So what the aim of this project is to try to combine the use of DNS and GCM, in particular of our code GHOST and WACAM with the thermosphere extension, to study the features, characteristic features of the MLTE. In particular, we are planning to do these 3 experiments. One is using GHOST in a configuration where its large scale corresponds to the smaller scale of WACAM, which is 20 kilometers. Then a second experiment where we will set GHOST in order to simulate as larger scales 100 kilometers in order to have an overlap between WACAM and GHOST. And the third experiment we want to perform is using the LES version of GHOST together with WACAM. And in all 3 cases, the initialization of the large scales for GHOST will come from the energy fluxes we will get from WACAM. So, okay, there are several questions we can try to address with these 3 experiments. The one I think is probably the most important is to try to have a complete assessment of the intermittency in the MLTE. The MLTE is very much stratified and is very intermittent, and it supports shears, and these shears are responsible for anomalies of the Ionosphere, which affect ultimately also things like the satellites communication or the GPS measurement. So we think that this is one of the cases where with the DNS we can provide very, very useful information, either to improve the parametrization in the model and to get direct insights on natural and real settings. So I'm done. Thank you.